Good evening. I'm Mike Wylczynski with Pangea Environmental LLC. I'm a certified professional geologist with over 40 years of experience, much of it in hydrogeology and mining. I've developed mines and held permit mines in my career. I've been asked to look at the available information, analyze it, and try to develop a picture of what the subsurface looks like beneath the proposed mine site and surrounding area. And that's what this presentation is going to be about. But before I get to that, I need to just explain a few geologic terms. The geological material we need to look at this site, there's three. Bedrock, this is the old hard rock that needs to be blasted or drilled. And it's hundreds of millions of years old, and we're not going to talk about it that much. These are things like sandstone and shale. Then there's the glacial material, and this is what we're mainly interested in. There's two types. One is till. This is clay rich and has low permeability, which means water doesn't flow through it very well because the clay fills all of the area or volume in between the other grains, and so water can't flow through it very well. It's also not good for sand and gravel because of the clay. It sticks to the sand and to the gravel, and it's hard to process off of it. This material is formed when the glacier ice just melts and drops whatever is entrained in the ice. So it's just a hodgepodge of material of all different sizes that can range from clay all the way up to boulders and house-sized boulders even. The other material is outwash or stratified drift. This is sand and gravel. This is what is mined for aggregate. This material, after being dropped by the glacier, was sorted and cleaned by running water from the melting ice. So all the fine-grained material got carried away, leaving behind nice, clean sand and gravel deposits. Because the fine-grained material isn't there, there's a lot of open space between the sand grains and the gravel, so water flows through here fairly well. So this is what it makes up our glacial aquifers, stratified drift or outwash. Also, it's where our wetlands are, lakes and streams. So it's quite ecologically important. A few photos I want to show that'll show what the glacial material looks like. This is up in Oakland County, and it's an area where they were doing some construction, and there was a long trench dug in down to about 30 feet and exposed the geology very well. The material above here is till. It has a lot of clay in it. You can see there's gravel pieces in here, larger pieces. And it's stiff. It forms straight walls. You can see how it even, these are from the teeth of the scrape of the bucket, leaving impressions on there. And then right below that is glacial outwash. This is sand. And you can see the big difference between it. This is the material that it makes the aquifers and that people want for aggregate. So what we have here is we're looking at an area where we had running water depositing the sand and gravel, and then a re-advancement of the glacial ice depositing the till on top of that. Quite interesting. Here we have some nice sand and gravel. You can see how discontinuous the gravel is. These occur as lenses. They're generally not large areas within a deposit. You can see how this one pinches out going in this direction. And here we have a view of the trench that was dug. Here we can see this overlying till, clay-rich till, and then underneath it is a nice glacial outwash or stratified drift. Right here, it looks fairly uniform in thickness, but this isn't always the case. Just a short distance from here, this clay till thickens to about 50 feet, rather abruptly. So in a glacial environment like this, changes in the type of material you have, and the thicknesses and that, change rather abruptly. It's a very complicated geology to work in. This looks rather simple right here, and is not typically the case, although this isn't that large of an area really either. When I was asked to look at this site, one of the things I looked at first is a topographic map, and this shows the contours of the elevations put out by the U.S. Geological Survey. And this is the one that includes Wilkinson Lake. Here's the mine property here. What I'm looking at here, here's a pond. Here's a pond right on the property at the surface. Here's another piece of surface water. Because these are such a higher elevation than the surface water here, we can assume these are perched on a clay layer, or a very good chance they are. And so that's what tipped me off to start looking further at the geology. And along that same line, went and looked at Eagle's wetland map viewer. Here it is for Wilkinson Lake. Again, here's the lake. These little green patches here, they're not regulated wetlands because they're not large enough, although they may be close enough to surface water that they may be regulated. However, they also indicate that there's water at the surface, groundwater at the surface, near the surface, and it's perched on a clay most likely. That's one of the ways we get wetlands. They perch on top of clay that is overlying more permeable material. So the next thing I did is start looking at the water well logs or water well records that are in Eagle's well logic database or water well viewer. And what they do is they tell you information about the pump and the casing and how it was drilled and how deep, and more importantly, the geology and depth of groundwater. So what I've done here is just looked at trying to differentiate two different glacial materials. One clay rich, which is your till. This is the material that's not very permeable, it's not good for sand and gravel, and it causes water to pond on the surface and also perch on it in the subsurface. And the other type of material is the glacial outwash or the sand and gravel, mixed of varying amounts. And so I've colored them brown. Is brown here, the clay and sand and clay, which has the clay in there, so I'm assuming that's a till. Then we have the sand and the gravel underneath it, much like you saw in the photograph that I showed earlier of that trench. So I've looked at a bunch of these in the area, and water well drillers are very good at differentiating between material that contains groundwater and material that doesn't. And here we only have two types of material they have to worry about, till and outwash. So these are fairly accurate. I've used these logs on environmental investigations. I've used them for groundwater exploration for municipal wells. And they're fairly accurate. They take a while to get used to some of the language the drillers use. It's not typical geology a lot of times. But in glacial outwash, it's fairly simple. It's either going to contain water or it's not going to contain water or not produce water. When you get into the bedrock, it gets more complicated. And it also depends on the drilling methods you use. And the wells that I've looked at use several different drilling methods. There's cable tool for one of them or two of them that is an extremely accurate old method of drilling water wells. So I believe the data is pretty good. We even have one that is from a hollow stem auger that is very similar to what is used in environmental investigations. So after looking at some of the water well records, I just plotted the thickness of the till that's at the surface at each location. And here's the mine site again, the proposed mine site again, right in here, Wilkinson Lake. And here, these are water wells that are in Eagle's database. And the footage here is the thickness of the clay at the surface, or the till at the surface, more correctly. So here it's 30 feet thick. That's overlying any sand and gravel. Here it's 80 feet thick. Here it goes down to 5. Here it's 21, 5, and 0. So you see it's fairly, it varies a lot in thickness. Here it's, again, you have 35 feet up in here, but then down to 0 here. So it varies very dramatically. And down here, 4 feet. So this is a material that is causing water to pond on the surface and form those little wetlands that I showed you in that pond. It's also a material that has to be removed before you can get any sand and gravel. That's a lot of overburden that has to be removed, and that's going to be problematic. Here we have an aerial photograph of the proposed mine site. Wilkinson Lake is off over here. And these are the same well locations that I showed on the previous photograph with the clay thicknesses or till thicknesses. Here's one that's right on the property, and two. To give you an idea, and here's the big cluster up here, and I'll show you, here's a map view. Here's this cluster here, that's over to here, and here's one, that's right here, and two there is right there. And so what we do in geology is we take those boring logs and we use those to construct a slice of what it would look like if we were to basically cut through here with a trench, kind of like a layer cake, and see what the geology is doing, what the layers are doing, what the layers of the clay till, clay-rich till, any outwash, and the gravel and things like that are what's going on. And so what I did is I'm going to do a cross section from well location 2, 1 to 4, just those 3 boring logs. And the way this is done is you look at the logs as I showed before, and we just separated it into 2 types of material. The till, which does not conduct water and which actually confines water and is not sand and gravel material. And then you have the outwash, the stratified drift, the sand and the gravel. Just those 2 types of materials we're going to deal with here. And what I've done is you then take those boring logs and you just take the elevations and plot those, location 2, 1, and 4, and the distances. And here's the approximate mine property right here, west going to east. And the elevations, I just kind of straight lined them. I'm not sure what it actually is between there. That's why it's kind of dashed. So then I put down what the material is. And in well 2, I found that there was till to this depth, till to this depth in well 1, and then in 4 till to this depth. Below that, in this one, we have gravel, and then we have sand. And then down here, this is where the well screen is, and that's where it's pulling the water for the well. And they're typically 4 or 5 feet in length for a home well. Here we have the till, here we have sand, and we have some gravel, and then there's no log. Nothing was recorded. And then the well screens here. So here we have the till, the clay-rich till, down to about here, and then the sand and gravel and the well screen. So then we just connect those contacts between similar material. So here's the clay till to clay till to clay till. And here's the gravel from here to here. We recorded it in this well. And down here it's this thickness, so that's the gravel. And all of this is the sand or sand and gravel down here. And here's the well screens. So this material up in here is material that will not conduct water very well. Water will tend to pond on the surface. It'll be a problem if you're trying to use infiltration to groundwater to get rid of any kind of processed water. And it really complicates mining. These thicknesses here are substantial for the amount of sand and gravel that you'll see is here above the water table. Okay, here I've just colored in the layers so they'd be easier to see. Here's the till, the clay-rich material that's fairly impermeable. Here's the sand or sand and gravel in the gray, and this is material that conducts water or is an aquifer. And here's the gravel. This is all just based on the logs from the water wells. And then I just connected the water levels in the wells and added the proposed mining level. And here we have what's called a water table, and that's because there's fairly dry material above the water table. Below the water table, it's saturated, and you can start pulling groundwater from it. Here, it's not. We don't have a water table. This is the material here, the sand that can conduct the water, is saturated right up to the base of the till clay, which is fairly impermeable. So there really isn't a water table. What this represents is the level that the water would rise to under the pressure if you were to put a well in. So if we were to put a well in here, you're going to have a water level here. Here it's right at the point where it'd be confined, unconfined However, water tables fluctuate several feet even within a year in some places. And so this could change. So in some cases, like here, you might have a confined aquifer, unconfined aquifer. What this causes is if you were to puncture this or go through that upper confining till layer, it's like opening a can of pop. You would have water pushing out through it. When I worked in consulting, I actually had a couple projects where we were looking at putting in deep foundations, and I had to determine if there were confined aquifers because they were concerned of puncturing the upper confining layer and having water starting to flow out of it. And this can cause a spring, a washout, and it can be quite disastrous. To also start changing the hydrogeology or hydrology of the area. All right, this is the final figure. All I've done here is put a blue overlay where groundwater would be encountered if you were to drill a well or try to mine. So everywhere where it's blue, you would encounter wet material. Well, except here. Here's the till is going to hold the water back, and you're going to encounter wet material to the base of the till. But if you were to put a well in here or dig a mine, this is where the water would rise to. So this leaves just a small amount of sand and gravel above the water table. And when you take into account that you need to stay 5 to 10 feet above that, it really limits the reserves that you have here, especially when you take into account the amount of overburden that's present. So this really shows demonstrates that the value problem, that there may not be value here. I don't think there's value that they can be mined at a profit staying above the water table. It also presents some very serious consequences that we've talked about with the confined aquifer and changing to hydrogeology, and problems with infiltration of any processed water, and even the well itself that's going to be used or proposed to process the mine could really impact the hydrogeology of the area. Our summary, based upon a review of readily available information, is that there's shallow groundwater, confined aquifers, and thick overburden will make mining difficult and likely not profitable. Much of the sand and gravel is saturated with groundwater and may require a hydrogeological study and permit from EGLE to mine. Very serious consequences may result from the mining. These include adverse impacts to nearby residential wells from mining and withdrawal of groundwater for processing sand and gravel. Potential flooding of the mine by penetrating confined aquifer or unexpectedly encountering a perched aquifer. Low permeability soils will make infiltration of waste process water a problem. Salt water or other undesirable naturally occurring contaminants could be drawn up into the fresh water due to the high rates of groundwater withdrawal. The quantity of groundwater needed may not be available due to the aquifer properties. Aquifer or the EGLE water withdrawal assessment tool does not take this into account. We welcome questions, and additional information will be considered. Pangea Environmental LLC, Mike Wylczynski, Certified Professional Geologist. Thank you for listening.